So the goal of this talk is to tell you about self-organizing Gaussians, so compression of 3D Gaussian splatting scenes. And hopefully by the end of the talk, you will have an idea of what's going on there on the right in this kind of teaser video that deconstruct these 3D Gaussian splatting scenes into grids. So the talk is about this paper from ECCV, Compact 3D Scene Representation via self-organizing Gaussian grids. That was a paper together with my co-authors Florian, Anna, and Peter. We are all at Fraunhofer HHI. To dive into the 3D Gaussian splatting topic, maybe let's take a step back. What is this all about? So the goal that is, or the problem that is solved is novel view synthesis, a really age-old problem in computer vision. So you get as an input a set of multi-view images that can be a few images or a few dozen or a few hundred, and you want a representation of your 3D scene that you can then move freely around in the scene, like we see on the right, where we have this lovely tree stump in a 3D Gaussian splatting representation, and we can look at it from all kinds of different views. And in the original 3D Gaussian splatting paper, they provided a really great quality of their results, but they didn't optimize for size. So the scenes were really large. In this case, this truck scene is 640 megabytes, as you can see on the left, which is quite a lot if you want to stream this or watch this on a mobile device maybe. And so in our work, the self-organizing Gaussians, we brought that down to under 30 megabytes, which is a 22x reduction. And as you can see in the side-by-side view, the quality of the scene stays pretty much the same. You can even see on the self-organizing Gaussians that some of the artifacts of the floaters from the 3DGS are gone missing. So that's a good thing. In 3D representations, you have different choices. So traditionally in computer graphics, you would have textured meshes, but they are really tricky to handle under some conditions, surface meshes. And then we have these point-based representations that you can kind of count the 3D Gaussian splats under the splat base. There's no really connectivity on any of this. Your scene is represented by these splats or circles. And it's really good to represent highly complex scenes. Everything is kind of happening on the surface of your object. There's nothing in between. There's no volume to it or anything. And a kind of resurgent of this field was started by the nerves, which you're maybe familiar with, was also an ECCV paper in 2020, which were considering this 3D scene reconstruction problem as an optimization problem using a neural network to do this, which leads to great quality, but is really slow to train and slow to render, and also is an implicit representation, so you can't really combine or edit this very well. This is what made 3D Gaussian splats such an overnight success when they were created as a paper in the summer of last year. If you look at the Gaussian splatting representation, your scene will be made up of millions of different of these splats. And so to characterize one of these splats, they have different parameters. They will have coordinates, covariance, opacity, and color, basically, to render a single splat. A technical detail is that the covariance is factorized into rotation and scale. But this is a bit abstract, all of this. There with a formula to render a single splat. Let's look at a representation, what you can actually do with the splats, how can they look. And so here I visualized giving different values to the scale parameters. So you kind of tiny like splats that are nearly point-like, and you have bigger ones that are more spherical or ellipsoids. And actually the scale parameter has 3 dimensions. So there is a scale in 3 dimensions, so you can create either points or lines, disks, or these ellipsoids onto kind of spherical kind of splats. And then you have the rotation parameter. So if you have a splat that's not a sphere, but something more elongated or a disk, then you can rotate that also in the space, in the 3D space that you have. There's the opacity parameter where you can fade in or fade out different splats. And then you have a color parameter where you have a base color in RGB or in the spherical harmonics DC components. Here visualized some splats from black to white. And then these spherical harmonics are an important part of the representation. they are there for the view-dependent coloring of your scene. So if you only have a base color, your scene will look the same from all directions. But if you want to model non-Lambertian effects, specularities, reflections, these kind of things that happen a lot in real scenes, you have to have a view-dependent effect in your scene. And the spherical harmonics is what's used here for the Gaussian splats. We'll see later in the talk why I'm going into detail on this. It's because these spherical harmonic coefficients make up a huge part of these parameters. So spherical harmonics, we don't need to go into detail about the math behind it, but it's a function that is defined on the surface of a sphere. So you can have a visualization from Wikipedia here, where you can see, okay, some components are, for example, looking on the left hemisphere or the right hemisphere of the sphere, and then you add more and more parameters that have higher and higher frequencies, looking at different splats from different directions. To make this a little bit more real, let's look at the left video over here, where we just have the base color for now. And if I start the video, I will fade in these spherical harmonics, and you can see how some of the view-dependent lighting gets faded in. We can see, for example, the table gets a little bit brighter on the one side from the reflection in the sky, and a bit darker on the other side. We can fade that out and see the base color again. And hopefully that should give you an idea a bit how these spherical harmonics work and what they're used for. We can also look on the other side, where we have just these spherical harmonic AC components, just the view-dependent effects, and don't have the base color anymore. And you can see, depending on the viewpoint that I'm looking at the scene, we have this component that changes and tells us something about where the light in the scene is coming from. As an aside, all these visualizations in this talk I made with SplatViz, which is a tool that Florian wrote. He's the co-author on this paper. And if you're a researcher or try to understand the Gaussian splats a little bit more in detail, or want to do some prototyping with them, I recommend that you check out this tool. You can see there on the left, there's a little edit field where you can type in some Python code to change your splatting scene, and then either during the training of the scene or after, investigate interesting things about your 3D scene. So it's a really useful tool. So we've now seen how these Gaussian splats can be parameterized. A little word on how the whole thing works. How do I get the 3D scene out of it? So we initialize from structure from motion. So we get a kind of point cloud with tiny splats out of it. And then there will be a differentiable optimization that takes the images that we saw as ground truth and then tries to adapt the Gaussian splats to match these images in our training set. And an important part also that's happening in the Gaussian splatting is this densification that will look at under-reconstructed or over-reconstructed areas. So places where Gaussian splats are missing, and will clone or split some Gaussian splats there to fill in the blanks over time. How does this look? So as I said, we need some calibrated cameras, and we start with a kind of point cloud in the beginning. So all the splats here are tiny spheres. This is this initialization from the structure from motion. We can look around the scene a little bit and then start the training, and you will see the splats immediately jump to positions and fill in the scene to make this 3D scene look like the camera positions that we put in there. You can see some jumps in the video. This is the densification process every 100 steps, where these splats get reorganized a little bit, and maybe you catch it at step 3000. It happens for a really quick time, but all the opacities of the splats are reset, and only the ones that are really important come back. And this was it. In the blink of an eye, it was gone, but you can see it here on the right side. So this is the training process of the Gaussian splats, which hopefully gives you a bit of an idea how that works. So, our Gaussians. We have 1 million of them, or maybe 2.5 million, and each of the Gaussian splats will have certain parameters. We saw the coordinates, which is 3 parameters, the scales, which is 3, the rotation, which is 4, the opacity is a single one, the color is 3, and then an additional 45 for the view-dependent effects. If we look at the resulting file, so this is the original Gaussian splatting uses a PLY file format for this truck scene that we saw earlier. It's in this case 630 megabytes, and then we have all these blocks of 10 megabytes, which is 2.5 million Gaussians. Each attribute is 4 bytes long, which is 2.5 times 4 is 10 megabytes. And we see here the view-dependent effects are 3/4 of the whole file is these view-dependent effects. Then we have a little bit of the color here, the FDC, the rotations, the coordinates. We even have some normals in there, which are all 0 and unused. Then the scale, and finally these opacities. So what can we do to compress this kind of stuff and make it more efficient? So yeah, I will put the numbers here for the truck scene. So we have 2.5 million Gaussians. We have these 62 different attributes like rotation and scale and so on, all of them 4 bytes long, which makes a total of 630 megabytes. One thing you can look at to compress is just reduce the number of Gaussians. Here is visualized removing some of the Gaussians by their opacity. And if you watch the line on the bottom, you can see that you can remove nearly 40% of the Gaussians without the scene changing at all. So there's a lot of Gaussians to get rid of that you actually don't have an effect in the final trained scene. Also, there are other methods like mini-splatting that focus on really reducing the number of Gaussians in the scene. So I created this slide last week, so it's horribly outdated because today mini-splatting v2 was put on archive, but you can see here 3D.js for the spike scene has 6 million parameters, and in the mini-splatting they get it down to 1/10 of that, only 600,000 Gaussians at the same PSNR. So this is a good idea to reduce your number of Gaussians. You have to do less. Another thing you can do is you can reduce the number of your attributes. We have these normals in the file that I talked about. We don't need them at all. You could also drop the view-dependent effects, so you get a 4x reduction doing that. We did some experiments with that in the paper, and you can see the numbers there if you're interested. Yeah. The scene still renders fine and it looks okay, but yeah, you lose these view-dependent effects and the reflections and so on. So it is noticeable, but maybe that's something you want to do. And there's another couple of details that I won't go into now, how you can represent other things with fewer parameters, but if you're interested in that, yeah, have a look at maybe these papers. And then the third component here is that we have 4 bytes for a float 32 value for each of these attributes. And this is not really needed. This can represent 4 billion different values. And yeah, we don't need that for most of these values. We can do something with really fewer, for example, these spherical harmonics. We can be fine with only having 32 different unique values for that. So overall, we can get to around maybe 6x reduction. It depends on how much quality you want to keep, but yeah, let's say between 5 and 6x for most scenes. You can do a reduction with quantization without losing any of the quality. Another way to compress things is looking at your Gaussians again, and you have 2.5 million of those maybe, and let's say 2.5 million different colors, and not all of them are going to be really interestingly different. And we can do some clustering and vector quantization. Looking at the example over here, we could cluster all the blue ones, all the green ones, and all the yellow ones, and then create a codebook where we say, okay, there's only one entry for blue, one entry for yellow, and then we assign only the indices to the Gaussians and say, okay, all the blue ones get index 1, and we look up the color here. We do use some of the finer changes in these values, but depending on the size of our cookbook, this is also a good strategy to reduce size in your Gaussian splats. And then finally, there's compression strategies that is just normal information theory, Huffman or arithmetic coding, where you say not all of your values will be evenly distributed. You will have some that appear a lot more than others. So yeah, give shorter code words to them and you get a 15% to 40% reduction for free. And with that, we've kind of exhausted all the traditional coding things that we can do for Gaussian splats. And now we have to think more outside the box and find other avenues to reduce this any further. And yeah, so now these things from the intro video come into play. Now we want to find a way to actually restructure these Gaussian splats. And in this case, our idea is to organize the Gaussian splats into a 2D grid. So we can see here a 3D rendering of this nice Lego piece, and then we can see how the whole thing gets organized, gets flattened out into a 2D grid. This is a bit maybe like if you're familiar with UV mapping for meshes. First we have this sparse 3D point cloud, and we want to find a representation where this is a 2D grid of the same data. So let's say you have 1 million Gaussians, maybe, so your n number of Gaussians is 1 million. And so we say you just reshape these values into a grid that's square root of n times square root of n. So 1000 by 1000 is your grid size. And then you have these 59 attributes. So you have maybe 59 layers of this kind of grid. And then if you look through those layers, you can find all the values to create a single Gaussian splat. So we didn't change anything about the data from the PLY file in this case. We just reorganized and reshaped our data into a different format. That can look like that if your Gaussians are not organized yet. So we just take the 3D Gaussians and visualize their color over here. And we reshape them into such a grid. And for this truck scene. And it will look like this. We get the Gaussians organized this way. And so the second part of the idea now comes into play. Compressing really noisy data leads to huge files, but compressing organized data with low frequencies leads to much smaller files. And so all these three images contain exactly the same pixels. They are just organized in a different way. So here in the beautiful Van Gogh painting, you can see them in the original order. Here it's a random order, and here it's a sorted order. And we get a large reduction for the completely sorted order over the random order with PNGs. And with lossy compression with JPEG, it's even higher, that we can get a 9x reduction of this random thing compared with the sorted version. So the quest becomes, how do we resort our Gaussians that we had in this kind of random order in our grid into a nicely sorted one that we then can compress with the image compression format. And actually this is a really tricky problem because permutations are hard. Let's say you have 6 points or 6 Gaussians. If we look at all the permutations, it's 720 permutations. And if we run this with 25 permutations per second, to look at all of them is 29 seconds in this case. So there's a lot to go on. If we increase this, it increases really, really quickly. So if you have 9 Gaussians, it's 300,000 permutations, and the whole video would run for 4 hours. And if you blow this up further to 5 times 5, it would take you 19,000 trillion years, which is a lot longer than the universe existed. So looking at all the permutations to find out which is the best one that has a really smooth function that is nice to compress, won't cut it. Of course, there are algorithms for that, but still the Hungarian algorithm, which is one to solve this linear assignment problem, has a n-cubed time complexity. So it's kind of fine to do that for 1,000 elements. You can do that in an hour. But if you have 2.5 million Gaussian splats, it would take you 500 years. So that's not good. And then we discovered the fast linear assignment sorting algorithm, which was out there, which can do tens of thousands of these assignments in a reasonable time. But if you throw 1 million at it, it will unfortunately not work. So we had to come up with our own solution. And the idea behind that is we want to go from this kind of randomly organized grid into a really nice and smooth one that has exactly the same values, just organized in a different way. And yeah, the goal is to reorganize, in this case, these pixels. And in the Gaussian way, it would be by looking at current state. Let's maybe look at this one over here and say, okay, we blur this current state and say, okay, this one would be really nice to compress if we could get to this kind of version. And then we make random candidates from all of these pixels, all of the entries in the grid. We group them into groups of 4, and then we do this blockwise linear assignment where we, on the GPU in really high parallelism, find a better assignment, switching out the 4 candidates to possibly 4 new positions within their group of 4. And we do this for all of these elements at once, finding random groups of 4, switch them out thousands of times, reduce our Gaussian blur size, do it all over again until we get from this really noisy selection to one that contains exactly the same values, just in a different order. Here's a video of the process. So on the right side, we have our values. They are really noisy, and then in the blink of an eye, you will see that they can snap into a position that is already quite sorted. And then on the left side, we have the smooth target, or ideal target, idealized target. And then we continue iterating more and more until finally we arrived at our final sorted grid. It looks a bit like a Milky Way kind of, like galaxy kind of thing, which is an interesting thing that happens if you reduce higher dimensional data into a 2D grid. So our parallel linear assignment sorting can arrange this high dimensional data in a dense 2D grid, and the neighbors in the grid will still be close in all their input dimensions. There are similarities in this with dimensionality reduction like PCA, but actually what our output is a completely dense grid. You don't get that with your usual PCA or dimensionality reduction methods. There are similarities to clustering as well, and there's a lot of inspiration from self-organizing maps. A technology from the 80s, which was the inspiration for this work. But this one doesn't work for millions of elements, and also we need to solve this, give each element its own place in the grid, which only PLAS can do. So how do we use this algorithm? We use it to sort our Gaussians by position, scale, and color. And it's important to realize that all the attributes need to be sorted together. So we need to sort the Gaussians themselves, not their color independent of their scale. That wouldn't work, then we couldn't render it anymore. So we sort by the most important ones, and then we enforce the smoothness on the remaining attributes, which the argument being if they are close in position, scale, or base color, then they also should be close in opacity, rotation, and view-dependent color. And coincidentally, this also reduces some artifacts and floaters in the scene like we saw before. We do this over the whole optimization process of the Gaussian splatting scene. And sorting 1 million Gaussians takes around 10 seconds, but still the training time overall will be nearly identical to 3DGS because we end up with fewer Gaussians in the end, because we said we can throw some of them away and we have different hyperparameters doing that. Our training method is one of the original 3D Gaussian splatting, but where we include this sorting step that takes the Gaussians reshaped into this grid times 59 space, resorts the values, and then adds the smoothness regularization. And finally, when we're done with the process, we can take our sorted and smooth grids and use 2D image compression and get a bunch of images that we can store on disk that has reduced the size of our results. So you have these 59 grids that you need to sort as 2D images and that you need to compress then. We are using JPEG XL for those, where we have one file per of this attribute group, like one file per scale and one file per rotation, and then one file that has 15 layers with each 3 colors for the spherical harmonics. And the nice thing about this is the decoding part is super simple. So The file format itself is super simple. It's just a set of images. You can, any kind of program, any kind of programming language has support for decoding images. It's super fast and super easy to do. The Python code for decoding our Gaussian splats is really short. You can just load them on disk, decode the images, rescale your Gaussians, reshape them, and you're done. That's a super nice thing, because all the compression part lives in these image compression standards that are decades old and have a lot of useful algorithms in them. And through our preparation of this organization of the Gaussians, we can leverage all of that and get this 22x reduction for the truck scene. And other scenes have between 15 and 14x reduction. It depends on the size of your scene. And when deactivating the spherical harmonics, you can get an even higher reduction in the scene. But as we said, you lose some of the fidelity. Since 3D Gaussian Splatting came out, a lot of people have been working on this problem, either compacting, that is reducing the number of Gaussians, or compressing the Gaussian splatting scene. And to be able to compare these different approaches better, we started this 3D Gaussian Splatting compression survey that you can find under this link. It's an interactive survey where you can find your data points, turn on and off different methods, turn on and off different data sets, and have a look on how they work. And it's an open survey, so it's hosted on GitHub, and we are in regular contact with the authors to add more of the data sets and more of the results there. Yeah, for us, this grid assignment PLS algorithm is optimal, but I think there's a little bit more headroom in classical coding. So I think if we combine more of the ideas of, for example, how to reduce the number of Gaussians, we can get even better results and even smaller files, which is an interesting thing to do. Personally, I'm also excited about dynamic Gaussians or volumetric video. I cheated a little bit on the right. That's actually not Gaussians. That is a dynamic instant NGP from a recording we did at our volumetric studio. Yeah, but it's something we're excited about to do, and I think this fits our organizing Gaussians approach really well. And then also in the context of maybe this Voxel 51 talk, this PLS algorithm is a new method to organize millions of high-dimensional data points into a locally smooth, dense 2D grid, which in this case we used for 3D Gaussian splatting compression, but I think it will be exciting to use this for maybe other things as well, and data visualization, for example. Yeah, one final word on other things we're doing with Gaussian splats. So this is work by Florian, the co-author of this paper, who's working on generalizing or generating 3D Gaussian splatting heads, which is an exciting topic to work on. So these are the kind of things our group is doing around Gaussians, so the self-organizing Gaussians in the compression, the splat with viewer, Florian, the 3D Gaussian heads, and the compression survey. And with that, we've arrived at the end and the beginning again, and hopefully now you have a bit of a better understanding of what's happening on the right there with these 3D Gaussian splats that get deconstructed into grids. Thank you.
Fantastic. Thank you, Wieland. So we do have 3 questions in the Q&A queue if you want to hop over there. And a reminder to folks is in the chat, I did already post some of the links that Wieland wanted you to check out, but we'll also include those in the follow-up email as well.
Can I see the Q&A while my screen is shared?
Yeah, if you want to kill your share, getting over.
Let me do that. It's not reacting to any inputs. Can you read the first question to me, maybe, while we're waiting?
Yeah. What is the first question is, what is the source of the floaters? So your screen has stopped sharing. What is the source of the floaters? And I think that was right around the time where you were showing the bulldozer or the dump truck in the Lego kind of animation. That's when that question came in.
Okay, so original floaters in 3D.js or in novel view synthesis generally happen from you don't cover all of the views of your views. So if you pick a view that's somewhere in between, you might see something that isn't actually there, where we as humans would say, okay, that cannot be that something floats there, but it's a perfectly good explanation for the two views that you saw there. That's for 3D.js, and for our method also from the smoothing, I guess it can happen sometimes that you would, from the smoothing, introduce some floaters on top, but we saw more it helping actually the compression and helping the scene quality rather than introducing any artifacts that made it worse. The second question is, how do your results compare with Niantic's SPZ compression? And the Niantic SPZ compression does all of the things that I explained as the traditional coding stuff. So all of the first 4 or 5 slides, the quantization, the organizing your Gaussians, this is kind of the stuff that mostly the quantization is mostly being done in the Niantic SPZ. So it's a traditional kind of coding. And also it can go well together with the self-organizing stuff. But yeah, it's more on a lower level. It's only covering part of the story than Niantic SPZ. Yeah. Let me go for the third question, which is a bit longer. So the question is about the spike animation, where we saw that we can remove some of the opacity Gaussians and not lose much of the quality. And yeah, it was a view that I randomly chose by loading up the scene to the viewer. So it was not a training view per se, it was just a random view. And actually we measured this as well. So with all the test views, we measured this, that you can lose 30% of the opacity Gaussians, so the smallest opacity Gaussians, without any effect to the PSNR, and 10% more with just a tiny loss. And then, yeah, that actually works for all the views. Okay.
I think you do have one last question here, and the question was, why does your technique eliminate some of the floaters? A bit of a follow-up to an earlier question.
So I think our technique eliminates some of the floaters and is nice because through this organization, we organize Gaussians together that lie on a surface. For example, for the truck, you can see the world is full of surfaces, but Gaussian splats will actually organize them pretty randomly. So you will have different layers of the Gaussian splats there, and we'll have completely random rotations and stuff like that. And by our process of putting these Gaussians together, organizing them in a way, and then smoothing out the result, we will get actually nicer surfaces and smoother functions, and thus remove some of the noisy stuff that is an artifact of the optimization process. And this is why our scenes can look more natural in the end.